Okay, so hello and welcome everyone to the seventh lecture of our CODA program. So brief recap about the previous lecture. So in the previous lecture, we delved deeper into the thread divergence issue, and we saw multiple programs, right? And we saw the number of steps. Sorry, is there any question? Okay, I guess there was some noise. That's okay. Uh, okay, so in previous lecture we saw that we delved deeper into the thread divergence issue, and we saw uh, we saw multiple programs which were having this thread divergence issue, and we saw the number of steps that were taken to execute those programs, and then we also step by step looked into how to remove the divergence from them, or at least reduce them. And then towards the end of that lecture, we also saw how, we also started with a new topic, which was memory. And we also saw that how a GPU, how the memory is organized on the GPU. Uh, we typically saw what is shared memory and all those things, and what is global memory, and where is all those memory located on the GPU. So yeah, so typically there we stopped yesterday. So for today's uh, so the today's agenda is to cover the cover the memory aspects in the detail. So we'll be looking into the GPU memory hierarchy in detail. Then we'll see few things related to bandwidth and latency. Then we'll also see what is latency hiding. Yeah, and then we'll probably go to the locality aspects, and and in the locality aspects, we'll see a couple of examples related to the locality, and yeah, probably there we'll stop today. Um, yeah, and yeah, so let's get started with it. So that's a brief outline for today's lecture. Let's get started with this. So this is where we left off in the last lecture. So if you remember, I told that this is the typical memory hierarchy of the typical memory hierarchy on the GPU. So at the lowest level, we have threads, and each threads have multiple amounts of registers associated with them. And then there is a shared memory which is per block, which is allocated to each block of the each block of the each block in the grid, and multiple such blocks forms a grid. And then there is a global memory which is common across all the threads in the GPU, as well as across all the grids. And the communication between host and device occurs through this memory, through this global memory. So whatever host wants to send to the GPU, it will first place it in the global memory. So if you observe one thing here, this memory hierarchy is very much similar to the computational hierarchy that we saw. Like there is a thread, and then there is it's within a thread block, and at the top level we have grid. So, so the key advantage of having such an hierarchy is that if we know such things, if we know about, if we are aware about this hierarchy, then we'll able to exploit it to get, get more performance out of, more performance out of our applications. So typically in this case, we'll be able to use shared memory to reduce the latency for our applications. And we'll see as we go along how to use all these things, shared memory and all those stuffs. Okay, yeah, so that's, that's quite similarity between computational hierarchy and memory hierarchy. So apart from that, yeah, we saw that, yeah, this global memory, which is also known as GPU's DRAM, or the video memory, as we saw in last lecture, and it's the main mean of communication, data communication between host and device. So whatever we did, like CUDA malloc and CUDA mel copy, and all those things to allocate and copy the data across CPU and GPU, was happening across, happening across something called as PCI Express bus, and the things were getting moved to and from the this global memory. So yeah, so it's a main mean of communication between main mean of data transfer communication between host and device. So everything that host want to send to the GPU will be placed in this global memory and will be taken from this global memory. And Yeah, so it is common across all the threads. I mean, if you even visualize multiple threads, then across all the threads of all the threads, this global memory is common. So that is something we should know. So if a thread wants to communicate with another thread across a grid, or I mean across multiple grids, or within the same grid, or within this or within, I mean across the multiple blocks, then it can do via this global memory. But within the thread block, if you want to do, then it will be better to do via shared memory. There is some noise from someone's side. I request others to mute unless you have any question. Okay, let me see what is there in chat. Okay, good evening. I request all of you to mute unless you have any question. If you have any question, then you can just unmute and ask. No issues with it, but please don't unmute just for, I mean, just during the presentation. If you have any question, then please feel free to unmute and ask. Okay, so there we were, and we see that the content which is present in this global memory is visible across all the GPU threads, across all the grids and everything. I mean, it's global across entire, I mean, all the threads. And since it's very, I mean, in the hierarchy, it's very far from the core, GPU core or streaming multiprocessor. Its latency is very high, across 400 to 800 cycles, which is actually high, because I mean, if you see other memories, you'll realize that it's I mean, lot more cycles than what those memories take. So latency is high, and throughput is around 200 gigabits per second. And I mean, what is throughput? As probably I mentioned this in last lecture, but it's the number of operations that can be performed in unit time. So in case of memory, it's number of reads or writes that can be done in a second. So it's and these reads and writes are, I mean, quantified using bytes. So I mean, how many bytes of data you are able to read or write in that particular time frame. So it's 200 gigabytes per second. So that's what it is. And one thing that I forgot to mention in the previous lecture was like this GPUs are like throughput oriented architectures. So this is something related to throughput, so I want to place it here. So what will happen is so memory latency for a single read or write access to the GPU's global memory, which is the DRAM of GPU, might be slightly more, or I mean, might be more than the latency which is required to access the CPU's global memory, or CPU's DRAM, not global memory, but CPU's DRAM. But when you talk about throughput, it's like number of operations performed. I mean, uh, okay, so the throughput would be throughput for the GPU's memory will be larger than the CPU's memory, because uh, throughput is something, the number of, I mean, is something which is quantified as number of operations which can be performed in per unit time. So like, even though the latency is less, I mean, latency is more for the GPU, so GPU will be taking more time to access global memory for one particular operation. But in general, GPU can club multiple operations into, I mean, can access multiple, I mean, it can do multiple access to the global memory at the same time, and hence the throughput is larger. So think of it like this: there are multiple reads and writes happening to this global memory, and which is ideally not the case for CPU. So like that's why the throughput is larger, because the number of operations performed are larger. So throughput wise, GPU's memory accesses are bad, but latency wise, CPU has lesser latency. So you'll see that CPU might take lesser cycles to access its DRAM. So that's one point that I wanted to highlight between CPU and GPU here for throughput and latency. And then we also saw like what is texture and constant memory, if you remember. So briefly, I'll reiterate what I said like in previous lecture. So both of these memories are read-only memories, as well as size is very less, like 12 KB and 64 KB for both texture and constant memory. But like so as the size is less and they are only the read on, I mean, they are only read-only memories, so they can't be typically used for storing large amount of data or performing any they can't be used to store our data on which we can perform the computation, because typically the applications that we generally use for the computations on GPU have very large amount of data. So instead of storing the real data, we can store the metadata inside them, or the something called as like something like the data that keep tracks of other stuffs or other data which we have stored in the global memory. So that part we can keep in texture memory or constant memory. So typically they are used for storing metadata, and the key advantage here is that their throughput is very high, like 800 Gbps, which is actually 4 times than the global memory. And talking about difference between constant memory and texture memory, it's that for texture memory, it is optimized for 2D spatial locality. I discussed like what is 2D spatial locality. So uh, for like matrix operation, it will not just it will optimize for the accessing its neighbors around that particular cell. So if you are accessing 3,3 in the matrix, then the cells that are surrounded by it, like 2,3, then 4,3, and all those will be accesses to all those will be quicker. So that's one speciality about it, which is not there in constant memory. So that's the difference between them. And talking about this position of constant and texture memory, they are at the same level at the global memory. So they fall somewhere in the, they fall in at the hierarchy somewhere here, like with the global memory only. So they are not per block or, so they are across the grid. That's what I wanted to say. Common across all the grids, as we have this global memory. Yeah, so that's it. I think that was a very comprehensive recap, I guess, for the previous lecture where we left off. And yeah, so moving forward, does anyone have any doubt up till this point? I'll quickly go back to the chat, otherwise I'll move on. Okay, I see there are no questions. So okay, so let's move on instead. So okay, so let us move on. So apart from these three things, which is texture which is texture memory, constant memory, and constant memory and global memory, we have three other things, which is L2 cache, L1 cache, which is also known as shared memory, and registers. So okay, L1 cache, which is shared memory, is shown here, as well as the registers, but L2 cache is not shown, which falls somewhere in between the global memory and the shared memory. So like it's common across all the threads, uh, like in the same way as it is for global memory. So it falls somewhere here. So common across all the threads, but size is very small as compared to the global memory. So if you see, the size of global memory will be typically, or size of the GPU's DRAM or the global memory will be typically typically you will see its size is like 12 GB or 16 GB, but coming to the L2 cache, its size is very small, like it's just 768 KBs, or at max some MBs it will be there. So that's what that's what is the size of L2 cache for GPUs. And one more point is, as I told, like it falls here somewhere, and it's common across all the threads. So if it's common across all the threads, then it's also shared among all the streaming multiprocessors. So one thing that you should observe here about the L2 cache, uh, the thing is like since it is shared across all the threads, uh, the number of the amount of memory or amount of L2 cache which is available per thread is very small, right? Because GPU has we can typically launch kernel with tens of thousands of threads, and even with multiple kernels. So in that case, what will happen is the amount of amount of memory inside the L2 cache that a particular thread has is has can be very less. So in that way, L2 cache might not be as effective as we have it on CPU, but still, we need this L2 cache. The reason is this fast atomics that it is mentioned here. So let us understand what it is. So Okay, so what is this fast atomics? So let us say, okay, let us say we want to synchronize two threads across different thread blocks, or even across, okay, across different thread blocks. Then for that we need atomics, right? And to implement atomics, we'll need a variable which can be tested and set, which can be whose value can be tested and can be set. So we need such kind of a variable, and that is how atomics is implemented. And we need to test and set its value atomically. And let's say we want to place such a variable, then place such a variable in memory. Then the best place to place that variable will be into the L2 cache, because L2 cache is closer than the global memory. So accessing such variable, or accessing such variable which are used for atomic implementing the atomic operation, will be faster, and hence like L2 can be used for implementation of something called as fast atomics. Okay, so I hope you got it. Like if you want to, I mean, if you want to synchronize between two threads of different thread blocks, we can't use shared memory because it's not common across, I mean, thread blocks. But you can use L2 cache because it's common across all the thread blocks and threads. And to synchronize, you need some variable, and to I mean, best place to place that variable will be in L2 cache, since accessing it will be faster as compared to global memory. So yeah, so that's what is fast atomics. So it helps in implementation of fast atomics and many more functionalities like those of fast atomics. So that's something about L2 cache. And yeah, so apart from that, yeah, so apart from L2 cache, we have this L1 cache, which is also known as shared memory. So there is, I mean, when it comes to L2 cache or shared memory, there are two things to it. I mean, first of all, first thing that you should observe is that it's a configurable 64 KB memory available per streaming multiprocessor. So this entire block, uh, I mean, it's named as shared memory, but in some sense, it's both L1 cache as well as shared memory, and its size is 64 KB. And what is this configurable? And why it is known as configurable 64 KB memory? I mean, the reason is that we can specify what we want. Like we can configure it in such a way that like we can tell, like I want 64. Sorry, out of the 64 KB, I want 16 KB for the shared memory and 48 KB for the L1 cache. So let us try to understand what is shared in L1. So shared memory is something which is controlled by the programmer. So you will see that programmer will be able to specify that, okay, I need this 16 KB as a shared and 48 KB as L1, or vice versa. I need 48 KB as shared or 16 KB as L1. So that is, I mean, that is something which is which is in the hand of programmer. Or we can also specify that 32 KB I need as shared, and 32 KB as L1. So, okay, so I mean, what is the difference between the shared and L1? First of all, we should understand that. So shared memory is completely, I mean, not completely, but it can be controlled by the program. It's programmable. It is controllable by the programmer. So you can specify that, okay, I want to declare a variable which should be stored inside this shared memory. So that is what is this shared memory, where this L1 cache, it is something which hardware manages. So you won't, I mean, as a programmer, you won't have control over that L1 cache, but yeah, the shared part you can typically, manage and control. So you can specify what variables should go into the shared memory. You can also specify that, like, okay, this array I want to place it in shared memory, or this vector I want to place it in shared memory. So all these things you can specify. Yeah, so that is typically the control that is given to the programmer to exploit the shared memory. And one more point, as I specified, it is also, I mean, a programmer can also control the amount of shared memory. So you can specify I need 16 KB of shared memory, or 32 KB, or 48 KB out of this total of 64 KB that is available. And yeah, so that's it. Yeah, so two more points. First is the latency of this shared memory or L1 cache is very, very low. If you see, it's just 20 or 30 cycles. Just compare it with the cycles needed for global memory. You'll realize that it has very low latency, or it is very, very fast. just a couple of cycles we need. And the reason is it is very close to the streaming multiprocessor or the core of the GPU. So that is the reason for the low latency. And since it has very low latency, its bandwidth is also very high. Across 1 Tbps bandwidth we can get. If we have stored some data in shared memory, then we can access it at this speed, 1 Tbps. Okay, so that is about L1 cache or shared memory. Next thing is registers. Uh, okay, yeah. So one thing I forgot to mention probably is that shared memory is per block. So uh, okay, so all the threads across one block will have common shared memory, and similarly, it won't be across all the threads. It will be per thread. Sorry, per block. Uh, so it is not common across all the threads. It is per block, and it is shared across the threads of a particular block. So so the thread, so this thread, so from this pictorially, this thread cannot access the shared memory of this block, and vice versa. So threads of the same block can access the content of the shared memory. But yeah, the other blocks shared memory are not accessible by the threads of this block. So yeah, that is other point that I wanted to specify. Apart from that, we have this registers, and you will observe that there are a lot of registers available per streaming multiprocessor. So typically 32K registers are available, number of registers are available in one streaming multiprocessor. And if you do some calculations, like if you have some threads per streaming multiprocessor, then, and if you divide it by this number, typically you will see that on an average you can have around 20 or to 21 registers per thread. And this is a good number, because as long as you have something in register, it accesses very fast, because register is something which is very close to the core, even closer than this L1 cache or shared memory. And its bandwidth is very high, as expected, because very close to the core of the GPU. So its bandwidth is typically 8 Tbps. And yeah, you should observe one thing, that these two components, L1 cache or shared memory, and registers, are something which can be exploited to get a very decent amount of performance, because both of them are very uh, close to the core of or the streaming multiprocessor. But another point to observe here is that the shared memory, not L1 cache, but shared memory is programmable. So you will be able to specify that, okay, I want this variable to go into shared memory. But for registers, that for registers this is not true. Like you won't be able to specify that I want this variable or particular variable to go into register. So it is completely dependent upon a compiler. So as long as compiler is able to uh, allocate register to a particular variable, it will do. Otherwise, it will spill to the global memory. Yeah. So, but in general, we should be able to exploit shared memory, and registers will be taken care internally by the compiler. And first of all, it will try to allocate the variables on register, and then it will spill. If then it goes beyond the capacity of register, it will spill into global memory. But in general, if you use these two things together, you'll be able to get decent performance, and we'll see how to do that. Especially, we'll see how to exploit shared memory in the upcoming lectures. Yeah, so that's it for this slide. Any questions? So far, any questions? I'll quickly go to the chat. Is global barrier we went over last time an example of fast atomics? Okay, yeah, yeah, so global barrier you can think of as a atomic operation across all the, yeah, but atomic is something like, let's say you have a variable and multiple threads are performing performing some operation on that variable, and you want to synchronize the access across all those threads. Then for that case, atomics is used. But barrier is slightly different. Barrier is something like a synchronization point inside a program. So until and unless all the threads have reached that point, no thread will move further. So I guess there is some difference between barrier and atomics, but I think going towards synchronization lecture will make it further more clear. So I'll partially say that, I mean, I won't give complete answer right now, but yeah, I mean, there is some difference, I would say, uh, as compared to fast atomics and global barrier. Okay. Tina is saying okay. Okay, yeah, that's okay. Any questions? I mean, please feel free to ask questions. Otherwise, it will become, I mean, just one-way talk or something like that. Because for today's lecture, there are, I mean, I don't have any like very interesting problems to solve. So it will more be like theoretical, and probably it will start feeling boring to you people otherwise. Anyways, unless there are any questions, okay, unless there are any questions, I'll move further with my slides. Okay, so we saw the typical memory hierarchy that we have for GPU. Okay, so we'll see in later lectures how to exploit this hierarchy. Typically, I mean, we'll see how to exploit shared memory. That's the main part here, because rest all is under the control of hardware, because registers we can't program and all this thing. Global memory we know how to access, and during computation we saw. Okay, so moving on. Uh, so let us talk about, I mean, let us talk about what is bandwidth and how it's typically associated with GPU and all those things. So when we talk about bandwidth, it's about, I mean, how wide is the data bus rather than how fast that data bus is. So when we say data bus in context of CPU GPU communication, it's that PCI Express bus that I keep on mentioning in a couple of lectures, right? So uh, okay, so yeah, so that's one thing. That's one PCI Express bus, and another thing is like there is also some uh, bus available for transferring data between, I mean, not transferring, but reading and writing the data between the CPU's core and the CPU's DRAM. So that's second thing, and also the L1 cache and all those things. I mean, the bus that is available to read and write data between that L1 cache, L2 cache, and that GPU's DRAM. So when we talk about the bandwidth, we talk about how fat or how wide that data bus is. Uh, the one that I talked, I mean, just right now. So how wide that data bus is rather than how fast it is. So let us take one analogy here. So when we okay, so let us take one analogy. Let us compare the airplane with the train, uh, with the amount of people it can transport, and the time it takes to transport them. So if you see with airplane, you'll be able to transfer fewer peoples from one place to another. Let's say transporting from place A to place B using aeroplane. I mean, transporting some people from place A to place B using airplane takes 1 hour, but it transports very less number of people, right? Typically, if you see, couple of hundreds of people can go from one place to another place using an airplane, but it is very fast. uh, yeah, so that's latency, that the time that is taken to transport the people is latency. So latency is less for airplane, but the amount of data or the number of people that is transferred from place A to place B is lesser compared to the train. In contrast, for train, the latency is high, right? Because time it takes to transport the person from place A to place B using a train is higher compared to airplane, but the number of people that are being transported from place A to place B using train is much larger. Probably thousands or even tens of thousands of people can be transported. So yeah, so that is what is bandwidth. So like the amount of data being transferred rather than the latency. So uh, when we come to bandwidth, I mean, yeah, so that's the amount of data being transferred, and that determines what is the bandwidth. And and bandwidth can be improved by parallel data transfer. So transferring more than one, I mean more than one block of data at a time from one place to, from memory to uh, core or something like that. And when we I mean, why we are talking about all these things? The thing is, GPU is somewhat like a, as I told, it's somewhat like a throughput-oriented data structure. So even though the latency is larger for, I mean, for any operation, for IO operation, let us take for transferring the data from GPU's DRAM to core is larger for GPU's DRAM to core is larger. I mean, it takes more time to read or write a particular data from the, I mean, from the DRAM to the core. But the number of data, I mean, number of chunk or number of data that we can read at a particular time is larger. That is what is parallel data transfer, and that's why the bandwidth of GPU is typically larger compared to the CPU's bandwidth, because here the fatness is larger. I mean, there is more fatness if you see the wide data bus is present rather than the fast data bus. But typically for CPU, it's, I mean, it's opposite. We have fast data bus, but the bus is not that wide. Okay, so that was about bandwidth. But there are a couple of, I mean, techniques proposed in literature for improving this bandwidth in general, just not across, I mean, not for the GPU or across CPU or GPU or anything. It's general techniques that are proposed for improving the bandwidth on any, I mean, any architecture or anything. So here are three techniques. First is like you can reuse the data. So what I mean, what is the reusing of data? So let us, I mean, let us talk about it in this GPU's context. So let us say we have this program where we have two arrays, and we are declaring two arrays, and then we want to perform some computation on both of those arrays on the GPU. So what we'll do is we'll transfer the first array from CPU to GPU, do some computation, we'll get back, I mean, get back the results, and then we'll declare the second array, transfer it from CPU to GPU, do some computation, bring its result back. But instead of this, we can do one thing. Let's say if the first array, after bringing its result back, is not being used further, then in that case we can just reuse that array by doing, like, instead of declaring the another array and then passing it to the GPU, we can just populate that first array itself and then pass it to the GPU. So in that way we can I mean, we can reuse the data rather than I mean, just declaring the new data. So that's one way. So that will save some bandwidth on the CPU. I mean, the transfer, I mean, data transfer bandwidth on the between the CPU and GPU, because we are just reusing that array on the GPU. So once that computation on the first array is finished on the GPU, we'll populate it on GPU itself and then we'll start reusing it. So the second data transfer is not needed. I hope you are getting it. If there is confusion, you can later ask it. But yeah, so yeah, so that's about reusing data. Then there is data compression. So coming to data compression, it's like this. So instead of transferring the entire data as it is across CPU to GPU, what we can do is we can compress the data and then can pass across that PCI Express bus, or I mean, yeah, across that PCI Express bus, the Express bus from CPU to GPU. So advantage of compression is that the amount of data transfer, I mean, the size of the data will get lesser, and the time taken to transfer it from CPU to GPU will be less, provided that the compression and decompression time are reasonable. So okay, so let me put it in this way. So let us say the amount of time taken to transfer uncompressed data was X, and the amount of time taken for compression and decompression together was Y, and the time taken for transferring the compressed data was Z, then Y plus Z should be less than X. So to see the benefit of compression, Y plus Z should be less than X. So that is one way we can exploit the data compression to improve the bandwidth. So in that way we can, I mean, we are transferring less data, and compression and decompression are also taking minimal time. So yeah, that is the way we can save some bandwidth using data compression. And the third way is to recompute instead of fetching and storing. So here, I mean, here what we do is like, what is the general way? Like we just transfer the data from CPU to GPU, do some computation, and then bring back. That is like first we store the data from CPU to GPU and then fetch the results. That's the conventional way. But this recomputing suggests something else. Like it's another way of improving the bandwidth. So in this recomputation, what we do is instead of storing and fetching the data back, what we do is like uh, let let us recompute the data. Recompute the results back. So let me put this with an example. So let us say we want to run some algorithm on the GPU. Let's say algorithm A, we want to run it on GPU. So what we'll do is we'll offload the data from CPU to GPU, run the algorithm on GPU. In meanwhile, we'll also run the algorithm one on CPU also. And instead of copying the result back from GPU to CPU, what we'll do is as we are recomputing, we'll get the results on the CPU itself, right? So that saves the fetching part. So that is one. I mean, that is the place where we are saving the bandwidth. Like we are not fetching the results back, and we are recomputing it on CPU. So that is one way we can save the bandwidth by recomputing. Yeah. So any questions up till this point? I'll just stop here because yeah. Okay, I see there are no questions. Anyways, there are no questions. Okay, someone has raised the hand. If you have any questions, you can unmute yourself and ask. Ramasamy, yeah. Ramasamy, you can unmute yourself and ask. Okay, I'm assuming that you don't have any questions, so I'm moving forward the lecture. Okay, so these are the typical techniques that are used for improving the bandwidth. Uh, and yeah, so moving forward, so let us talk about latency now. Like we saw that um, latency is the time taken to perform that particular operation, right? So but coming to memory, it is time taken for the IO. Like here, the operation that we are performing is IO. When we see from the CPU or GPU core perspective, it is the amount of time that we need to, perform read or write operation. And for CPU or GPU core, IO, accessing the global memory or accessing the DRAM of CPU or GPU is it's one form of IO only. So here latency is time required for the IO. More precisely, the latency here in this context, the latency is the time taken for read or write operation. That can be either on L1 cache or L2 cache or the DRAM of the GPU or CPU. So ideally, ideally we want this latency to be zero. Because we just don't want the core or the processor of CPU or GPU to wait for the data. uh, but as we all know, the data transfer from DRAM to CPU or GPU core takes time, and yeah, that is something that can't be avoided because of the way this DRAMs work. And so one thing, the latency ideally should be zero and should be minimized if it is not zero. Uh, but it is not always the case. Memory becomes the bottleneck many times, because if you see the number of cycles taken for fetching the data from memory and bringing it to the CPU or GPU core takes, as we saw, like it takes around 400 cycles, right? In two slides back we saw that it takes around 400 cycles. So ideally, the processor should have the data available in no time, but that's not the case. It takes multiple cycles, 400 cycles or 800 cycles, up to 800 cycles it takes to fetch that data. So this thing can become a bottleneck. This memory IO can become the bottleneck on CPU as well as GPU in both architectures. Uh, but uh, but this latency, latency should be hidden in some way. And can anyone suggest what is the way using which we can hide the latency on the CPU? I mean, uh, just a quick Q&A. Like, do people know? Do people know how can we hide the latency on the CPU, or typically how it is done on CPU? Latency hiding. Okay, let me go to the chat quickly. Okay, we have question here. Yeah, that is correct. I mean, if we are not getting results from the GPU, then what is the purpose of using GPU? That's correct. But this is not, I mean, as I told, this is not, I mean, it's not typically for CPU, GPU, as I told earlier. This is, I mean, this, let me go back to that. This all these techniques that I'm talking about are generic techniques. Just I gave the example of that CPU GPU because we are currently in the CUDA context, so that's why I gave that example. But you are correct. What is the point of using the GPU if we are not, I mean, using the results from GPU? That is correct. But if you see, the results are computed on the GPU, and if we don't want to fetch that results, and we want to save that bandwidth, then what we can do is we just can run the I mean that algorithm on CPU and get the results. So that was what I was trying to say. Okay, I hope that clears the question, clears your doubt, Vasantha. When you mean by store and fetch, it is between CPU and GPU. Okay, so it can be between CPU and GPU. It can be also between CPU core and its DRAM. It can be between GPU core and its DRAM. So I mean, we can read and write from either. I mean, either of the case, right? So that's one thing. So there are multiple cases here. It can be applicable for multiple cases. Okay, here there is question, sir, if hypothetically latency for a data bus is 0, then we would never need to use CUDA device synchronize. Okay, it's not that we would never need CUDA device synchronize, because let's say we are able to transfer the data between CPU and GPU in no time. Let's say latency for data transfer between CPU and GPU is 0. And even let's say that GPU core gets the data from DRAM in no time. Let's say latency is 0, completely 0, hypothetically. But what can happen is thread might take a lot of time during computation. So when we launch the kernel, the computation aspect is also one thing, right? So if computation time is very large, then in that case CPU might not wait, right? If there is no CUDA device synchronized, it might start executing the instruction that are after it. Then in that case also there can be a problem. So it's just not about that data transfer. It's also about the computation part, like what time each and every thread takes to finish. Okay, parallel reads. So in what context is it, Varun? Parallel reads.
Essentially, parallel data transfer, it's the answer. Like you asked the question, right? How can we hide the latency of the GPU being so high?
No, okay. So my question was slightly different. Let me go back to the. Okay, so my question was like how this. I mean, how this latency hiding is done on the CPU, not GPU. We are not currently talking about GPU. Let us just talk about CPU, right? How this latency hiding is done on the CPU is my question. Let me go back to the slide. Oh, sorry, chat. Parallel reads. That is true for I think GPU, but for CPU it might be different because on CPU we have very few number of threads, right? So parallel reads, I don't think, I mean, will help much. Asynchronous programming. Okay. Is there anything else that we can exploit on CPU? You people know. Like, is there anything special we have on CPU that we can exploit? Yes, that's correct. We can fetch into the cache. That's important point. So caching is one thing. I mean, one definite point which we can. I mean, one definite thing that we can exploit to reduce the latency on CPU. Then other points, I mean, please feel free to discuss. I mean, what are the multiple ways in which we can hide the latency on the GPU? Sorry, CPU, not GPU. Again, sorry, CPU. Okay, I guess there are no responses. Okay, so there are multiple ways in which we can hide the latencies on CPU, memory latency on CPU. One is definitely caching. We can have a hierarchy of cache like L1, L2, L3, L4 cache. We can up to L4 cache. We can have like some of the architecture. Intel architectures have up to L4 cache. So that's one point. So whenever a block of memory is accessed from CPU's DRAM, we can place. We can place that block of memory in either L1, L2, L3, or L4, or in that hierarchy. I mean, in those caches, and whenever next time that block, I mean, word from that block of memory is being referred by the CPU core, it will get quick. I mean, it will be able to fetch it quickly from this caches. So that's one way. Second way to hide this latency on CPU is using multi-programming or multi-threading. So instead of just running one process at a time, what this CPU does is it places multiple processes in its DRAM. So advantage of it is like if let's say one process goes for IO, then it can schedule other process on the CPU for the execution. So that is one way in which it can hide the latency. So let's say there is one process which is requesting requesting some word from DRAM, then let that process perform IO operation or accessing that DRAM. Meanwhile, CPU can place I mean it can schedule some another process for execution. So that core is not idle. CPU core is not idle. That is one way. Second way. Then there is something called as write back caches. So in write back caches, what we do is just we write the word in the um, L1 cache and just and then just CPU moves on. I mean, it doesn't wait for in writing into the writing into the DRAM and all those. I mean, the lower level. Lower level things. I mean, lower level memory chips. So in that case, what will happen is when that word or that block will get invalidated, it will be written into the DRAM. So that's one way. Third way, and other points are like we can also exploit like parallelism, instruction level parallelism. So let's say we have one instruction which needs IO, then we can we can just let that let that instruction perform IO. But at the meanwhile, let's say we have that the next instruction after it, which doesn't which is not dependent on the previous instruction. So in that case, we can schedule that instruction for execution within the same process. So that is one way in which we can do by exploiting the instruction level parallelism. And then there are other ways also, like we can use pipelining. Like if you people have heard, there is something called as pipelined architecture. So in pipelining, what we can do is like there are the whole hardware is divided into multiple components. Like there is ALU, then there is one component for ALU, then there is another component for reading and writing and all those. There are several components. One is just for fetching and decoding the instruction. So multiple units are there. And let's say if one unit is busy, then we can still use the another unit and can exploit the parallelism that is there in the hardware level. So that is the way we can exploit. We can reduce the latency on the CPU. So these are some of the ways in which latency hiding happens on the CPU. At the CPU level. Okay, so I'll just move on from here. So yeah, I have talked about multiple ways, but the primary, or I can say the core way of reducing the latency on the CPU is through this memory hierarchy, which composes of registers, then L1 cache, then L2 cache, and L3, L4 caches, and then DRAM. So that's primary way in which the latency hiding can be done on CPU. But on GPU, if you see, we can do latency hiding up to some extent using this registers as well as L1 and L2 cache, as we saw in the previous slide. Latency hiding can be done up to some extent using registers and L1 and L2 cache. But the problem here is that the number of threads that we have on GPU are, very large. So the chunk of L1 and L2 cache as well as the registers that we will get per thread will be very small. So so what will happen is, like, we won't be able to store sufficient amount of blocks into this L1 and L2 cache when it comes to GPU, and hence latency hiding using L1 L2 cache and registers is not that effective as it is with the CPU, because CPU has, it has very few threads compared to GPU. And so if there are very few threads, then the per thread L1 and L2, per thread memory available in L1 and L2 cache will be much higher. And if that's the case, then this caching effect will be much significant, but that's not case for GPU. So yeah, so latency hiding can be done using this caching, but it's less effective on GPU. So instead of this, to make it more effective, what we do is we exploit something called as massive multi-threading on GPU to hide this latency. The latency of accessing the DRAM can be hidden by using something called as massive multi-threading. And let us see what is this massive multi-threading. Okay, so let us see how the latency hiding is being done. Let us say that this is the timeline, and this let's say this from this line to this line, this distance represents the 1 unit of time. So this is 1 unit of time, then this is second, then this is third, and then fourth, and so on. And here y-axis shows the time, x-axis we have the blocks. So this is one block, and let us say it has some computation to do. So sorry, okay, so yeah, so it has some computation to do. So let us say that this blue box represents the computation that that particular this thread block wanted to do. Let's say it did some computation, and then it waited for IO. So this that IO operation is represented by this stall, something called a stall. So it did 1 unit of computation, and then it waited for IO. And please note that this entire thing is for one streaming multiprocessor. Let us say that the thread block was executing on that streaming multiprocessor, and it did 1 unit of work, and then it went for IO. So now that streaming multiprocessor is completely idle. Now what it will do is it will take some another thread block and will start executing it. It will start executing its part of computation. So let's say after this thread block went for IO, streaming multiprocessor picked the other another thread block and started executing it. So let us say that this second thread block that streaming multiprocessor picked up also had 1 unit of work, and it did that work, and again that went for IO. This block even went for IO. But okay, so now we have this both blocks which are performing IO at this moment here at the third unit of time. So if let's say we have sufficient number of blocks, then this process can continue. So streaming multiprocessor can pick the third block, and it can execute uh, its part of computation, and let's say then again it went for IO, and it can, if that's the case, then it can again pick the fourth block and start executing its computation part. And yeah, again if it goes for IO, then yeah, then in that case we have all four blocks which are now at the IO. But it might happen that meanwhile the fourth block has, streaming multiprocessor processor has finished fourth block computation of the fourth block. The uh, IO operation of the first block might be finished, and it might start again executing its part. So this streaming multiprocessor might pick up this first block and will start executing it. So you can see here. So one thing that you should observe here is that streaming multiprocessor is not idle. At some point in time, let it be this or this or this or this or this, it is executing some of, it is executing something, some computation from at least one of this thread block. So you can see that even though the thread blocks are going for IO, the the streaming multiprocessor is being utilized at its best. I mean, it is not getting, I mean, idle. So that's one point that you should observe. And this is how we do latency hiding on the GPUs by exploiting the massive multi-threading. So here we are exploiting the multiple thread blocks that we have allocated per streaming multiprocessor to hide the latency. And if you remember, couple of lectures back, I mentioned that one streaming multiprocessor is being allocated multiple thread blocks for the execution. And this is the reason why it is being allocated multiple thread blocks, because it helps in latency hiding. So if, let's say, one thread block goes for IO after doing some computation, some chunk of computation, let's say it goes for IO, then that streaming multiprocessor can pick up another thread block and start executing it on its course. So yeah, so that is the advantage of latency hiding. So yeah, and one point that you should observe here is that this way of executing in this manner can lead to superlinear speedup. Does anyone know what is this superlinear speedup? Okay, I repeat, like, does anyone know what is superlinear speedup? But first of all, do you have any questions at this slide? I mean, something that you didn't understood from what I tried to explain. Just quickly go back to. I guess there are no questions. Then okay, if there are no questions, then the latency becomes. Yeah, I think this is quite close. I mean, latency divided by number of executions. So uh, I guess there are no other responses. Then in that case, let us move back to the slides. Okay, so let us try to understand this superlinear speedup. So what will happen is, like, let us assume in naive fashion what will happen. So in ideal case, what was happening? This block. Let us take this block. How many units of time it was taking to get? How many units of time it was taking to finish the execution? So it was doing one unit of computation, then 3 units of IO, then 1 unit of computation again. So 5 time units were needed for this block to finish its complete operation. And similarly, there are 4 blocks, right? So ideally, we would have needed 20 units of time, right? Total 20 units of time we would have needed to complete to complete all the computation of these 4 blocks. But if we go in this manner, if you closely observe, here first block will finish here, then let's say second block finished here. So 1, 2, 3, 4, 5. Second block will finish somewhere at 6. Third block will finish somewhere at 7, and fourth block will finish somewhere at 8. So if we see, ideally it would have taken 20 units of time to finish if we just executed sequentially without latency hiding. It would have taken 20 units of time for these 4 blocks to finish. But by using this latency hiding, we'll just finish in 8 units of time. So that is what is superlinear speedup. Like, we are able to scale the performance by using this latency hiding, the principle of latency hiding. I hope it's clear. If you have any questions, you can quickly post in chat. Just let me check. Okay, I guess there are no questions. But in case you have any questions, then please feel free to unmute or post them on chat. Okay, if there are no questions, I'll move further. So, okay, I'm assuming that you people have understood what is latency hiding and superlinear speedup. So moving on, let us talk about locality. So we all know that locality is very important on CPU, right? Because let us say that is how the caches are. I mean, that is why the caches are designed, right? So let us say that we have we have but we have accessed one particular word inside a block from the DRAM. then it is, I mean, it is highly likely that we will access that block, I mean, that word or something that from that word, sorry, something, some another word from that block in the future. So, so that is why these caches are designed, and whenever we access something from that block, from the DRAM, that block is placed in the caches on the CPU. So this so I mean, so that is how, I mean, that is what is locality principle. Some and the caches are designed to exploit this locality thing on the CPU as well as on the GPU. We saw like there are L1 and L2 cache. So locality is important on CPU as well as CPU. But yeah, so it is important on CPU as well as CPU, and all thread in the thread block accesses their L1 cache as well as the L2 cache. And yeah, so if you see typically the size of L1 cache, which I talked in the couple of slides back, which is also known as shared memory, uh, is of the size 64 KB on Pascal GPU. And as I also previously mentioned, that it is configurable. So you'll be able to mention, I mean, as a programmer, you will be able to mention that I want 48 KB of L1 cache and 16 KB of scratchpad memory or shared memory. So the 16 KB is under your, I mean, under the control of programmer. So you'll be able to specify some variable to go into that shared memory. And this 48 KB, if you specify it as L1, then it will be completely managed by hardware. And yeah, so threads in this thread blocks can use this L1 cache. And up to some extent you can also I mean, you can also specify that I want to use this L1 cache for storing this thing or that thing or this variable or that array or something, uh, which can go into the scratchpad memory. And it is configurable, as I told, like I mean, you can specify what chunk of scratchpad memory and what chunk of L1 cache you want. It can be either 1648, 4816, or 3232 for scratchpad and L1 cache. Yeah, so that's part for the L1 cache. And yeah, so typically as a programmer we should exploit this locality, because when, I mean, let's say you have some portion of array, or let's say you have a very large array, and there is a small portion of that array which is being accessed repeatedly by your application. Then in that case it will be very intuitive, or it will be very performance friendly to place that chunk of array, or that part of the array, or uh, uh, that stride, or that part of the array into the scratchpad memory that we can, I mean, that we can program. So in some sense programmer can exploit this locality uh, by using the scratchpad memory and L1 cache. uh, on CPU and GPU both, I mean, both we can do this. But in GPU setting, there is one more thing. There is one more locality called as spatial locality, which is very crucial. And we'll see why this spatial locality is crucial when we'll come to memory coalescing. There will learn like how the spatial locality among warp threads helps in reducing the memory excesses, or how it can help in grouping the memory accesses together into one memory access, and all those things we'll learn. Yeah, but on GPU, this special locality is something which is very crucial, and we should keep this in mind, and we'll come at this point later during coalescing. Any questions up till this slide? Quickly, I mean, go back to chat and see if any one of you have any questions. Sir, as a programmer, how do we decide whether to use L1 or L2 cache? Okay, first of all, Harish, I think L2 cache is something which is not in our hand. Like we can program up to L1 cache. I mean, we can either specify, I mean, okay, let me put it in this way. Like you can say that I want this variable or this array to go into L1 cache, which is scratchpad memory. But you can't specify that I want to place this variable in L2 cache. It is decided by hardware. So L2 cache is not, I mean, something which is in our hand. Only L1 cache, and not entire L1 cache even. The part of it which we call it as scratchpad memory is in our hand. I mean, is in the programmer's hand. So that point you should note. But yeah, this L1, L2, L3, L1, L2 cache are inherently exploited by the GPU's hardware. So whenever you try to access some chunk of memory inside the GPU's global memory, if yeah, so that will be placed into the L1 cache and L2 cache to improve. I mean, to get the benefit out of it. So if next time if we are accessing the same, I mean, accessing some word from that same block, then that access will be faster. Okay, so scratchpad memory is the same as shared memory. So okay, let me reiterate. So there is something called as L1 cache. So that L1 cache is divided into two parts. One is L1 cache. I mean, one is the L1 cache itself, which is managed by the GPU's hardware, and second is called as shared memory or the scratchpad memory, which is something which is in the hand of programmer, and we can program it in the sense that we can specify that I want this array or this variable to be stored on the scratchpad memory or the shared memory. I hope that's clear. Is it safe for programmer to use L1 cache? No, I mean not L1 cache. I mean it's scratchpad memory which is being programmed by the programmer, which is just small. I mean, it's a part of L1 cache. L1 cache is not being touched. So, okay, there is some confusion in case. So, L1 cache, L2 cache, all these are not programmable registers. L1 cache, L2 cache. Only part of L1 cache, which is called as scratchpad memory, is given to the programmer uh, for I mean storing some variables or something. I hope that's clear. Okay, so uh, okay, before moving on, I'll specify one point here. Caching and all those things are implicitly taken care by hardware, but here something like, I mean, some portion of cache is given. I mean, some portion of cache is provided to the programmer uh, for, I mean, for our advantage. So we can exploit that thing. Otherwise, this L1, L2 cache and all those things, registers and L1, L2 caches are, I mean, not programmable by us even on GPU. So that point you should always note. That's taken care by hardware. I hope that's clear. And if there are any further questions, please feel free to ask. Okay, I think I should move on from here. Okay, so there are, I mean, let's come back to CPU again. So there are two types of locality on CPU. Can quickly anyone tell what are that two forms of locality on CPU? Quickly, there are two types of locality on CPU, which are, I mean, which we generally talk about when it comes to CPU. I want you people to quickly tell what are those two forms of locality. Yes, one is spatial locality. Then there is also another form of locality, which is very often, uh, which is very often used on. I mean, which is very often specified on the CPU, which is being exploited by caches. Okay, I guess there are no responses. Yeah, Rishikesh. Temporal locality is another. Yeah, so there are two localities as by Gokul and Rishikesh. There are two types of localities on CPU. When it comes to CPU, there are two forms of localities. One is spatial locality and another is temporal locality. So let us briefly touch upon what are these two locality. I mean, two forms of localities on CPU. Uh, so what is spatial locality? So spatial locality tells that let's say I have an array and I have accessed its ith memory location. Array's ith memory location I have accessed at particular point in time, or let's say I have accessed that ith memory location. Then it is likely that I'll also access some I plus kth memory location where k is some sort of delta, like it's like it's some constant number. Let's say 10 or something. So if I have access some memory location inside the array, then it's or inside some data structure, then it is likely that I'll access the memory which is close to it. That is spatial locality. So I'm I'm seeing it from the space point of view. So if there is some access at some particular point in the memory, then it is likely that I'll access some close by memory which is very close to this memory location which I have access. So that is spatial locality. Second is temporal locality, which talks about, I mean, which looks into the time aspect of this locality, which says that if I have accessed some memory location, let's say ei inside the memory, uh, then inside that array, if I have accessed some memory location, then it is likely that I'll access that memory location again. So it is something like time aspect of the locality. So let's say if I have accessed that memory location uh, once, then it's likely that I'll access that memory location again. So that is the temporal locality. And let us look at the examples of both of this. So let us come to temporal locality first. So let us say I have this for loop. This is CPU code, sequential code, and let's say I'm accessing that array of I, which is ith location in the array or in the memory, some location in the memory, and I'm first of all I'm writing to it. So here I've accessed it. Then again I'm accessing it for reading as well as writing, and then again I'm using it for reading. So if you see here, I've accessed it once, then I'm re-accessing it here and here. So that is what is temporal locality. So it says that if I have accessed a memory location once, then it is likely that I'll access it in the near future again. So it would be accessed soon again. So that is what is temporal locality. And second thing is spatial locality, which says that if I've accessed a particular memory location, then it is likely that I'll be accessing the nearby memory locations. So this is the example for it. So here, uh, the loop goes from 0 to n, where n is some, let's say, some large number. Then if I'm accessing, let's say, array of 10, then I'll be also accessing array of 11, 12, 13, 14, 15. So I'm in some sense accessing the nearby memory locations in that array. I mean, so this array is stored as contiguous, I mean, is stored contiguously in the memory. So if I'm accessing the 10th element in that array, then 11th, 12th, 13th, 14th element will be contiguous in that in the memory. So yeah, so like when I access that particular memory location, I'm also accessing its neighbors. So that is what is spatial locality. And the caches are designed in such a way that they can exploit both of this locality, temporal as well as spatial locality. So whenever you will access some memory location, either on CPU or GPU, it will bring the entire block of that. I mean, whenever you access some word inside the DRAM of either CPU or GPU, it will bring entire block in which that word is present to the cache, which might be L1 cache or L2 cache, so that so whenever in future if you access that memory location or its neighbors, it will be present in that block. So that is what is temporal and spatial locality. And both CPU and GPU are, designed to exploit this temporal and spatial localities. But crucial point here is that these localities are applicable on CPU and GPU, as I told, but they are more applicable on CPU, because as I told, on GPU we have large number of threads, and the per thread cache available, per thread memory available for cache is very limited, and hence this locality, this both of these localities are more applicable on CPU rather than GPUs. But there is one aspect related to the spatial locality, which I have already mentioned, which is memory coalescing. That is something, it's very close to the spatial locality, which gets exploited on GPUs to improve the, to reduce the latency. And we'll see in probably in tomorrow's lecture what is that memory coalescing. And yeah, so probably, yeah, so let us do this classwork. Okay, so first of all, any questions till this point? I'll just quickly, okay, there are no questions. Okay, then let's move on. Okay, so we have this classwork, small classwork, like these are two snippets of codes and both of them does one particular thing, which is matrix multiplication. So here A, B, C are three matrices, and we are multiplying matrix A with matrix B and storing the result in matrix C, if you can see here. And both of them does this operation correctly, which is matrix multiplication, but there is small change in, I mean, both of them. Like here first there is J loop and then there is K, and here first there is K loop and then there is J. So interchanging of loop is being done between these two. I mean, that is what is the difference between these two. I want each and every one of you to try out. I mean, each and every one of you to tell me which code is better, considering that we are using row major order uh, for uh, for storing the arrays in the or matrices in the CPU as well as GPU. In this case, we have CPU, so let us assume that we are using row major order for storing the matrices on CPU. Considering that as a fact, or which of these code snippet is better, or which one will give better performance. Okay, I'll pause here for some time and let you people to think about this. Okay, I'll just okay. Jaya Raman is saying that first one. Okay, I request others to try. I'll switch back to the slides. Request others to try. Let me go back to the chat. Okay, depends on size of n relative to p. First one. Okay, Anish and Prashant are saying first one. People is saying depends on size of n relative to k. Okay, let us assume that size of n, p, and k are same. Let us assume that. Just for the sake of simplicity, let us assume that this n, m, and p are all are of same size. Then which one will be better? Okay, Abhay is telling first. Okay, okay. So you people are trying to go with the first. I mean, first option. Then let us assume that the first one is better. Then can anyone give some? I mean, uh, give some convincing argument why the first one is better. Like, you need. I mean, can you give some explanation for it? Like, why you are telling that first is better? Either you can unmute yourself or can just paste your answer in the chat. Let me go back to the slide so that you can just refer to it. Why the first one is better? If you are telling it's better, then why? I think it will be bad idea to compare temporal and spatial locality. I mean, uh, C uses temporal, maybe uses spatial. Okay, let me go back. Okay. Well, if you're telling that C uses temporal, actually it is using both temporal as well as spatial. If you see, because if you see, J is changing faster than I, so in some sense it is going along the rows. So it is also using spatial as well as the temporal, both localities it is using. So I don't think that that is a very correct way to compare. I mean, and even for A and I mean A we will be using spatial, but yeah, I mean that's not correct way to compare it. Like I didn't completely got your point. Like and let us assume that A, B, and C are either using temporal or spatial locality. Then in that case, it is also true for this one, right? This code also uses temporal and spatial locality for A, B, and C in some sense. Then I mean, how is it better? I mean, how this is better? I mean, I really didn't understood the point. Okay, I guess I think I should now move towards the explanation. Okay, so the answer to this is like the second code snippet is better because I'll explain why it is better. So if you carefully see in this both of this code snippet, there are three matrices. First of all, A, B, and C in both the cases, and if you need to observe one thing here, that in the first snippet, the C and A are being accessed in row major order, and I initially told that the array stored, I mean matrices are stored in row major order. We are assuming that we are storing matrices in row major order on the CPU, that is on that is on its DRAM. So accessing them in row major order will give us caching benefit, or more precisely it will give benefits due to spatial locality. So here C and A both are being accessed in the row major order. If you see, the first variable, which is I, is progressing slow, and the second variable J is progressing fast. So it is moving along rows. So that is the row major order. This is being accessed in row major order. A is again being accessed in row major order because I is the slow changing variable, but K is very fast changing variable. So again it is in row major order. But if you see B, it is being accessed in column major order. The K is fast moving variable. So its accesses will be in the columnar manner. So P of 0, 0, 0 will be accessed, then 1, 0 will be accessed, and 2, 0 will be accessed. So we'll move along the column for B. But for A and C, we are moving along the row. And as we are storing array matrix in row major order, this both will give caching benefits, but B will not give caching benefits. So that is one point that you should note here. Now coming to second code snippet. Here, let us analyze what is happening. Here, C we are accessing in row major order, right? Because I is slow moving variable, J is fast moving, very fast moving variable. So Ij will be in row major order because 0, 0 will be accessed, then 0, 1 will be accessed, then 0, 2 will be accessed. Okay, so this is row major order. Then again, this Ik is row major order if you see, because I is slow changing variable, K is fast changing variable. So here also 0, 0, 0, 1 in that manner will move along rows. And again for B also row major order if you see, because K is slow moving variable, J is fast moving variable. So again, the array B is also accessed in row major order. So here all three A, B, and C are accessed in row major order. And as I told that we are storing this matrices in row major order. If we use, I mean, if we use the second code snippet, then we'll get better performance, because obviously all these three are being accessed in row major order. And since matrix is also stored in row major order, the spatial locality will give us some benefit as compared to this first snippet, and hence this will outperform this first. I mean this time taken for this second snippet will be much lesser than this first snippet. And if you time this, you will see that first snippet takes 9.5 seconds and second snippet takes 4.7 seconds. So that is the reason. And one small another reason is also that this B, which we are accessing in column major order here in first snippet, is actually very fast. We are uh, accessing it in very quick manner, right? Because K is the innermost loop and it runs for every I and J. So we are doing column major order very frequently, and column major order it won't give us caching benefit because our matrix is completely stored in row major order. So that is one biggest disadvantage here, that that will I mean that will cause performance to degrade here. This thing will cause biggest performance degradation, and definitely this second snippet will win. If there are any questions, I'll uh, quickly go back to chat and probably will, yeah. C uses temporal and AB uses spatial. Okay, I really didn't understood. There is no point of comparing temporal and spatial locality. So either it's temporal locality or spatial locality. It will get some benefit from caching. So you just can't compare temporal with spatial. It's about whether it is getting benefit or not is the question out of caching. It might be either temporal or spatial. Whether it is getting or not is the question. Is what we should focus on. Spatial locality, first one, Cij, A and B benefits from spatial. For each ij. Okay. Sir, could you explain BKJ from code 1 once more? Okay. Okay, let us go to, yeah. So let us understand this again. So just let us focus on this BKJ. What is happening here? How is this being accessed? If you see carefully, how is this being accessed? How this matrix is being traversed? Let us see. So K is a very fast moving variable, right? Because it's innermost loop. So it will run for each and every value of ij. So how we are accessing this B matrix? So we are accessing it in this manner, right? For let us say for the 0th value of j, k will go from 0 to p, right? So let us say p is 10. Let us put some random numbers, right? So let us say that p is 10. So it will go from how it will go, like it will go from 0 0 0 1 0 2 0 3 0 4 up to 0 9, right? Because p is 10, so from 0 to 9 will go. So 0 0 0 sorry 0 0 1 0 2 0 3 0 up to 9 0. So the way we are accessing it is in columnar order, right? So 0 0, then 1 0 is the next element in that column. 2 0 is that is further next element in that column. So we are accessing it in like in column direction, not in the row direction. And as I mentioned, as I added that prerequisite that matrix is stored, matrices are stored in CPU on in row major order. This will not give caching benefit, because if you are accessing something in column major order, then you won't get benefit out of spatial locality. That is the problem. Like spatial locality is something that if you are accessing particular memory location, then all its neighbors are brought into the memory. And since the matrices are stored in row major order, all its neighbor will be that row elements. So row elements meaning, like if you are accessing 0 0, then 0 1 0 2 0 3 and 0, let's say 0 6 up to 0 6 will be brought uh, into the cache, but 1 0 will not be brought into the cache. So that is the disadvantage, and you are accessing it in column direction, where the benefit that we'll get out of spatial locality will be only when we'll go along the rows. I hope that's clear. Yeah, I hope that's clear, Gokul. Yeah. I think someone has raised the hand. You can unmute yourself and ask the question. Sir, what happens if BKJ takes place of BJK takes place of BKJ in the first one? then which one is faster? Okay, BKJ. Okay, I got it. What happens if BJK takes place? In that case, I think all three are in row major order, and I think the performance will be very much comparable to this second snippet. Second one, because in that case all three are being accessed in row major order. So there might be some difference in performance, but it will be very close to this. But here you can see that performance difference is, I mean, huge, right? It's almost double if you see. So first snippet is performing is taking double time than the second snippet. But if you change this kj to jk, then performance will be comparable for both. I'm not sure what will be the exact number, but I am thinking that the performance will be almost similar for both the programs, because in that case all three are being accessed in row major order. So yeah, I hope that clears your question, Abhay. Yeah. If you have any further question, then you can ask.